We present a deep conjugate direction method, or DCDM, for iteratively solving linear systems. DCDM is a novel deep learning approach to approximate the solution of large, sparse, symmetric, positive definite linear systems of equations. These types of systems arise from many problems in applied science. For example, they arise in numerical methods for partial differential equations. We use our algorithm to solve the discrete Poisson equation and a regular grid-based discretization of the pressure equations that arise in Chorin splitting technique for the inviscid incompressible Euler equations. The incompressible Euler equations are presented on the left, and the advection projection scheme proposed by Chorin is on the right. We discretize the pressure Poisson equation using a standard 7-point finite difference stencil. The right-hand side is discretized using the macro discrete divergence finite difference stencil. The discretized pressure Poisson equation is a large, sparse linear system which can be written as Ax equals b, where x is the unknown pressure. This symmetric positive definite system is commonly solved by the preconditioned conjugate gradients method. The pressure Poisson equation varies with different boundary conditions. We denote A omega to be the discrete Poisson matrix associated with the problem-specific voxelized domain. In the left image, we illustrate a sample flow domain in 2 dimensions with internal boundaries represented with blue lines. In the middle image, we voxelize the domain with a regular grid. White cells represent the interior or fluid, and blue cells represent boundary conditions. In the right image, we illustrate the non-zero entries in an example matrix A omega from the voxelized grid for 3 example interior cells colored green, purple, and brown. Each case illustrates the non-zero entries in the row associated with the example cell. All entries in rows corresponding to boundary or blue cells are 0. We use a data-driven, iterative approach to approximate the solution of the linear system. Our approach is based on line search minimization of the matrix norm of the error. We search and update the kth approximation along directions d sub k, where each direction is approximately the optimal one, a vector parallel to A omega inverse times the residual. The step size alpha sub k is chosen to be optimal that minimizes the A norm between x sub k and the exact solution. We summarize our algorithm here. In each iteration, we predict search directions using deep CNN. The predicted search directions are not necessarily A-orthogonal, but there is strong evidence that A-orthogonality accelerates residual decrease. Hence, we impose the A-orthogonality between prior search directions to improve CNN predicted search direction. In our experiments, we observed that A-orthogonalizing with previous 2 search directions is sufficient. Lastly, we update the kth approximation x sub k in the direction d sub k. We train our network using unsupervised learning with a loss function equal to the L2 difference between an input vector and the matrix multiplied by our network evaluated at the input corrected by a scalar. We train using only the A01 cubed matrix associated with the full fluid domain with no internal boundaries. Our network only approximates the inverse up to constant scaling, and our loss function accounts for this by choosing a corrective scalar by minimizing the A norm of the error given the network-generated direction. In our algorithm, our network needs to approximate the scaled matrix inverse for residual that arise in the iterative approximation. We observe that for many flow problems, these residuals are skewed to the lower end of the spectrum of the training matrix A01 cubed. Therefore, we create our dataset using approximations of the eigenvectors of the matrix. We use Rayleigh-Ritz vectors since they approximate the entire spectrum of the matrix, but with significantly less computational costs than the full eigendecomposition, which can be expensive at high resolution. Notably, our network generalizes to all other matrices arising from more complicated flow domains such as A omega. Here we illustrate the architecture of our network. It consists of a series of convolutional layers with residual connections. In the upper figure, we show the residual block structure where the first layer directly affects the last layer with an addition operator. All non-input or output convolutions use a 3x3x3 filter, and all layers consist of 16 feature maps. At the middle part of the first level, we downsampled one layer via one stride average pooling, and another set of convolutional layers is applied with residual connection blocks. And then the last layer in the second level is upscaled and added to the layer that is downsampled. The final layer in the network is dense with a linear activation function. The first convolutional layer also uses a linear activation function. All other layers use ReLU activation functions. Differing resolutions use differing numbers of convolutions, but the fundamental structure remains the same. Notably, the weights trained in lower resolution can also be used in higher resolutions as well. On the left, we present residual plots with CG, ICPCG, deflated PCG FluidNet, and DCDM at frame 150 for the smoke-passing bunny example. Dashed and solid lines represent results for 128 cubed and 256 cubed grids respectively. DCDM reduces the residual in significantly fewer iterations. In the right table, we report convergence statistics for DCDM compared to the standard iterative techniques CG and deflated PCG. For both 128 cubed and 256 cubed grids with the smoke-passing bunny example, we measure the time and the number of iterations required to reduce the initial residual of a particular time step of the simulation by 4 orders of magnitude. DCDM offers significant speedups, particularly at high resolution. We demonstrate DCDM on 3 increasingly difficult examples. In the first example, smoke enters the domain through inlet boundary conditions in a circular portion of the bottom of the cubic domain. This example uses a grid with resolution 256 cubed, representing over 16 million unknowns. Next, we demonstrate flow past a complex static geometry, the Stanford bunny. This example also uses a computational grid with resolution 256 cubed. Finally, we demonstrate flow past a dynamic geometry, a rotating cube. This example also uses a computational grid with resolution 256 cubed. For each linear solve, DCDM was run until the residual was reduced by 4 orders of magnitude. Visually plausible and highly detailed results are achieved for each simulation. Thank you.